We have transformation. This is a brief summary. So let's put the BS up here for brief summary. Okay. Transformation from V to W, defined by transformation of the transform vector. The vector you get when you transform V is A times V, where A is this matrix. And clearly, V is going to have to be a vector in R2. Okay, if it's a real vector, if it's an Rn, it's an R2. Because you have rows of length 2, they have to multiply columns of length 2, so V has to be a column of length 2. And any vector that you get is going to have length 2 because you have 2 rows, and each row gives you one of the numbers in that column. So in V, you're going to get vectors with 2 components. In W, you're going to get vectors with 2 components. So T takes R2 to R2. Now, if we reduce the matrix, I'll put the word reduce in there, so that's how we're getting from here to here. We get this, complete reduction, okay? Meaning that the row space has a basis consisting just of this vector, 1/1/2. So the row space basis is this, and the column space basis is the column of this matrix, which corresponds to the column of the leading one here. So that'll be your 4, -6. Okay, so there's a basis for the column space. Now, we easily establish, and we have, that every column of the matrix will appear in W. For example, if you multiply this matrix by the vector 1, 0, you're going to get 4, -6. You're going to get the first column. If you multiply it by 0, 1, you're going to get 2, -3, the second column. You can check that out and convince yourself that the columns will appear over here in W. Now, a basis for that space just consists of one vector, okay, which means that this column vector must be a multiple of this one, and clearly it is. It's half of that one. Okay, well, there's your column space basis. Here's your row space basis. The other thing is, if you multiply any vector in the row space by the matrix, you're going to get a vector in the column space, right? So we're going to put the row space over here, the column space over here. Now, the reason we put the row space over here comes apparent when we find the null space. So we find a basis of the null space. Okay, the null space is also called the kernel of the transformation, the null space of this matrix. Either way, whether you regard it as a null space or the kernel, they pretty much mean the same thing. Null space applies to the matrix, kernel applies to transformation, but the matrix defines this transformation, okay? AX equals 0. X, then, any solution to this equation is a vector in V that maps onto the 0 vector of W. Well, AX equals 0 with this matrix instantly gives you the equation 4x1 plus 2x2 equals 0, and the equation -6x1 minus 3x2 equals 0. Okay? Where x1 and x2 are the components of x. So x is the column vector, x1, x2. Well, it follows then very simply that x2 is -2x1. And this follows from the first equation. It also follows from the second equation. If you solve either equation for x2, you get this. That means we've got kind of a free variable t. So if x1 is t, x2 is -2t. As a result, the vector x1, x2, or the ordered pair x1, x2, however you want to state it, is of the form x1 is t, so that's t, x2 is -2t, so it's of the form t, -2t. It's not written real clearly here. But that's then, factor out the t, it's t times the vector 1, -2, meaning that the vector 1, -2 is a perfectly acceptable basis for the null space, the space of all vectors that map to 0. Now, you got to prove that that's a space. We've got to prove that the column space is a space. We've got to prove that the row space is a space. But they are, and this is how we depict them for R2. We'll generalize this soon. Well, then, we can sketch our null space. 1, -2 is a basis, so their null space consists of all vectors that correspond to points on this line. whose terminal points are points in this line when their initial point is the origin. Okay. Well, all the vectors defined by this line map to the 0 vector. So the whole null space, this whole thing, maps to the origin of our space W, of our R2 space W, okay? And there's much more that can be said, so we're going to kind of go over here and say it. Now, before we go on, we're going to observe one property here. It appears that this row space can be modeled by a line that has a slope of 1/2, and the null space by a line that has a slope of -2. Now, what do you know about a line with slope 1/2 and a line with slope -2? Well, they're perpendicular. The slopes are negative reciprocals, something that we understand perfectly well. Okay? Well, we digress then. I want to introduce the concept of orthogonality because, as it turns out, for any linear transformation, the row space is orthogonal to the null space, and this has some implications that we kind of sketch out here in the case of R2 to R2. Dot product of two vectors in Rm. How do we do a dot product? Okay, I'm defining a dot product here, and this is my definition. It's totally consistent with the definition you have in your text, but that's actually a better definition to use. But for right now, since we are new to the dot product, I'm just going to define it like this. Two vectors. You express one vector as a row, you express the other vector as a column, and you multiply the row by the column. Nothing to it. Okay, now obviously the two vectors have to have the same length, but that's okay. I mean, between the row space and the column space, they're both spaces in the same vector space, so they will have the same length, they will have the same dimension. Okay? Now, I'm going to say vectors are orthogonal if and only if, or by definition, they're orthogonal if the dot product is 0. Okay? Well, let's look at the dot product of this basis vector, basis of the row space, and this basis of the null space. Okay, well, we take the 1 1/2 vector, express it as a row, take the 1 -2 vector, express it as a column, multiply the row by the column, you get 1 times 1, 1, 1/2 times -2, -1, add them up, you get 0. They're orthogonal. Orthogonality is a generalization of perpendicularity. Okay, in R2 and R3, orthogonal is totally equivalent to perpendicular. But in other spaces, in some more abstract spaces, they aren't RNs, although they're isomorphic, as we'll see. It allows you a finite dimensional. The whole concept of orthogonality, and even the angle between two vectors, which can also be defined in terms of the dot product, still holds, okay? Even though you might have R47 and, R36. Okay, well, anyhow. We then take a general vector in the null space, the row space, some constant multiple of 1 1/2, and some constant multiple of 1 -2. We're not going to use the same multiple. They might be the same, but they aren't necessarily. And we get the vector c over 2 multiplied by t, -2t, and we see if we multiply that out, we get 0. Just another illustration of orthogonality, okay? So, row space is orthogonal to null space. That's true for any linear transformation over spaces where you can define a dot product. Okay. The other thing now, let's extend this picture. And this is supposed to be a brief summary, and it's getting a little unbrief, but okay. Here's our transformation again. Our row space and our null space. Row space I put in purple, null space in yellow. And over here in W is the column space. That's in purple, okay? I put it in purple because the entire row space maps to the entire column space. And the entire column space could be pulled back to the entire row space. For every vector here, there's a corresponding vector here, okay? Actually have what's called a one-to-one mapping between the row space and the column space. And here's your null space, okay? The entire null space collapses down to the origin because every vector in the null space gives you the 0 vector, and the 0 vector over here in W, is depicted by the origin, is identified with the origin, the 0 vector. In the row space, I didn't want to draw a bunch of purple vectors, but this purple, and it's not a vector, but this purple arrow, curvy arrow, just indicates that the entire row space goes on to the entire column space in some way, depending on the transformation. So null space goes to 0, the row space goes to the column space. And also, the column space can come back to the row space. So I could put a kind of a double arrow on this. They have the same dimension. We've established that. We understand that. Okay, well, what about a vector? Because R2 consists of points that aren't on this line or this line. Most of the points in R2 aren't on one of these lines. They're out here somewhere else. So what if we got a point, say, out here? Where does it map? Well, it has to map to the column space. Well, let's look at this, okay? So the picture got a little complicated, but you can always go back and look at the original video. We have a vector to this point, okay? Now this vector can be expressed as a sum of a vector VR in the column space and a vector Vn in the row space. Because this vector Vn could also be drawn over here in order to add these two up, make a linear combination of these two vectors that's equal to the vector V. Now where does this go? Well, it depends on the transformation, but it goes somewhere in the column space, and it turns out that it goes to the same place that VR would go. And it turns out that every vector, the vector from the origin to any point on this line, goes to the same point of W that this VR vector goes to. Okay, because, why? Well, this vector V is a V equals a VR plus a Vn. Vn's in the null space, VR is in the row space. Well, then T applied to V equals T of VR plus Vn. Okay, that's easy enough. Well, this is a linear transformation. Okay, you can prove that any matrix-defined transformation of this nature is linear, and you should be able to prove that. Okay, by linearity, this is just T of VR plus T of Vn. That's the first property of linearity. The transformation of the sum of two vectors is the sum of the two transformed vectors. Well, T of Vn is just 0 because Vn is a vector in the null space, and the whole null space maps onto 0. Okay, so that's just equal to T of VR. Well, that's going to be true for the vector to any of these points along this line. It's going to be VR plus some vector from the null space. And it's going to have to map to the same point. So I'm saying that all the vectors along this green line here map to some point. Now it turns out that point's going to be more like down here, but we're not going to worry about that. We're not going to worry about exactly where it is. The point is that all these points give you vectors that map onto a vector whose terminal point is here. So every one of the points on this line is identified with this point over here by the mapping.